Right. So let's go to the assignment that I give you on the matrices. Um, so far there is a three sets of write up, which I hope you have actually viewed at least the first one. So the first one is as shown on the slot on the screen now. So this is a matrix, a 3 by 3 matrix. This is also known as a square matrix. So what I want to do is since you have learned this matrix linear algebra in a previous semester, so what we can do is to kind of like go through uh, the important things that you need to know about metrics. Um, and what I expect is that you will be able to do some simple things with the matrices. For example, if I ask you to find the transpose of the matrix, the inverse of the matrix, the determinants, and so on, you should be able to do, right? So these are rather basic, so I think we can go through it very quickly. And also, you must also know how to use matrices in order to solve problems. For example, if you have a linear set of equations, and then you can actually use matrices to solve it. And in fact, sometimes it is easier to use metrics to do these kind of problems, right? So here we go to exercise number one, which is I give you a matrix A given like this, and I ask you to find a few things, right? So I'm not sure whether you have come across these terms. Most of them you have come across, but maybe one or two probably slightly new to you, probably. So let's go to the first one, which is the element A12, A32, A21. Any I think you can do, right? So element refers to the specific value in the matrix. Okay, so I think you do remember you have A, I, J. I refers to the first number here, which in the subscript, the I is the row, and the second number is a column, right? So let me just shift it. Let me just. Okay, right. So A12, this is row, two is column. So A12 is A12. So this is 0. A32, A32 is row number 3. So 1, 2, 3, 1, 2. So this is -1. Okay, and A21 is row number 2, 1, 2, column number 1. So this is 6. Okay, right. So let's go to the whiteboard, and this is easier to do on the whiteboard. Let me just stop sharing. Okay. Let me see. Right. So I hope you see the slides here on the whiteboard. So this is element. You know what is the element. So now you want to find the minor. So minor, you have to differentiate between the minor versus cofactor, right? So do you know the difference between the minor and the cofactor? Can you recall what is the difference between the two? So minor, they ask for minor of A22. Tahu tak beza antara minor and cofactor? What is the difference between a minor and a cofactor? Minor tak ada sign. Very good. Nabila. Nabila or Shahida? Let me see. Shahida. Right. So a minor is without the sign. So minor in this case, A22 is over here. So you will have a T. So you only have 2, 1. So here you have a minor over here, so you cancel this one, so you get 2, 1, 2, 1, and this is 2, 0, right? So this is going to be 0 minus 2, so this is negative 2. So this is the minor of A22. And then when you want to find the cofactor, you will remember that you start with positive, negative, positive. So this is negative, positive, negative, positive, negative, positive. So this is positive. So in this case, your minor and your cofactor is the same. Okay. So thank you, Shayla. Right. So next one, transpose. Transpose. This is very straightforward. Transpose means you change from a row to column, or column to row. So in this case, 262, this you're going to shape it to column, and 0, 5, minus 1, you're going to change it to the column, the second row, sorry. And then 130, you're going to change it to the third row. Okay, so that is a transpose. Conjugate. Conjugate is very easy. Also, conjugate is the same like a complex number. You can take the conjugate, that is, you change the sign of the imaginary part. Okay, so if you look at here, you do not have any imaginary part, so your conjugate and your actual matrix is the same. Okay, inverse. So do you remember how to find the inverse? Inverse. So inverse, you find inverse of a matrix by finding for the determinant, right? And then here you want to find the cofactor which you have already transposed. Okay, so in order to find the inverse, you have to look for the cofactor of each element. So in this case, the element A11 over here, the cofactor is 0, minus 3. So this is 3. So here you will have a cofactor which is in this case. So in this case, this is this times this minus this, so this is 3. So in this case, this is 0. This is here, so you have 0, 0, minus 6. So but here you have a minus, so you have minus 6, and you do the others. So then you have a cofactor matrix, and then after that you need to transpose it. So you transpose from the column matrix to a row, from the column to the row, and get this. And then you will get the inverse matrix. Okay. Satu tu bukannya negatif 1. Let me see. Let's see. Minus 1. Right. So minus 1. Sorry. Thank you. Right. So 2, 0, minus 1, 2, 6, 5, 3, 2, minus 1, 0. Right. So let me see. What's the difference now? No. So you do the remaining, and then you will get the inverse. So I think this is straightforward. So I don't have to choose. I don't have to show everything. Thank you, Alice, just for the information about the matrix. Right. So now inverse, I think there is no problem. Trace. Pernah dengar trace? A trace. Tak. All right, Alice. So a trace is very easy. A trace of A means that I will sum I. So I means I start with, let's say this is a 3 by 3 matrix, so I will sum it up from 1 to 3. So then this means that I will take A11 plus A22 plus A33, right? And this will tells you that this is simply the sum of this diagonal elements. Okay, so in this case, the trace of A is going to be 7, 2 plus 5 plus 0, 7. Okay, so this trace sometimes it is used, especially easily, I mean, how to say, it is more commonly used when you have diagonalized the matrix. So let's, you will see in the later part of the exercise that you do have to find matrices, what we call that, the diagonal matrix. So let's say, for example, you have, let's say you have a D over here, and then you have a matrix at, let's say, -2, 1, let's say 2, and then you have 0, 0, 0, 0, 0, 0. So this is a diagonal matrix, right? Because the others all are 0 except for the diagonal part. And then in this case, the trace of D is very straightforward because you know these values, these are just the eigenvalues of your matrix. Okay, after you have diagonalized, let's say for example you have A, after you have diagonalized it, we'll assume, okay, you have this matrix. So in this case, your eigenvalues are -2, 1, 2. So the trace of this matrix is simply -1, and -2 plus 1 plus 2. So this is equals to 1. Okay, so that is the trace of the matrix. Okay, so now let's go to the next one. What did I ask from you? Hermitian unitary singular matrix. So Hermitian singular unitary. Okay. Right, so this is trace. Nice, finish. Hermitian matrix, pernah dengar Hermitian matrix? Yes. Hermitian unitary singular. Yang mana yang you tak pernah dengar? Hermitian singular unitary. I think all of them you pernah dengar kot, eh? Right, Hermitian is very simple in this case. So Hermitian, it means you have, let's say, H, but in this case you have A, T equals to A. So if you have an original matrix and then you take the conjugate of it, so what it means by conjugate, you have to take the complex conjugate. So this is complex conjugate. Yeah. So and then you have to take the transpose. So here, sorry, I should have mentioned this. I'm looking for complex conjugate. Right. So sometimes they call this as the adjoint matrix. So here you take the complex conjugate of the matrix, and then you transpose them. So this will give you the yes, adjugate of the matrix. So which I asked here, which I forgot to write. E. I asked you to find the adjugate. So adjugate, sometimes they use adjoint or adjunct of the matrix. So this is the adjugate or adjunct of the matrix. Okay. So unitary, on the other hand, normally unitary matrix people denote or represent it by U, because U means unitary. So unitary matrix, you have like this, right? A unitary matrix is a matrix that when you take the adjugate of it, right? This is going to be the same as the inverse of the matrix. Okay. Okay, boleh semua. Sorry. And then the next one is singular matrix. So singular matrix, sudah dengar? Singular matrix. Singular matrix is a matrix that you cannot invert. Okay, a matrix which you cannot invert is known as a singular matrix. And here, when you have a singular matrix, when your the matrix determinant is equals to 0. Okay, so where is that one? So remember we talked about the inverse of the matrix. So here you have a determinant of A divided by the AC, the cofactor of the matrix. Right, the cofactor of matrix A, and then you transpose this. So if determinant of A is equals to 0, so you see that this is not possible. So in this case, if you have this kind of situation, then A is a singular matrix. Okay, right. Okay, so I guess that sums up question number 1. The last one, which is to find the determinant. Determinant, I think this is no problem. But just to recap, to find determinant, you have to find the cofactor, right? The cofactor of all these, the first 3. Let's say for example, you start with the first 3 columns. The first row, you find the cofactor of it. The cofactor of this multiplied by the element itself, plus or minus depending on the cofactor, the second term and the third one. Okay, so that will give you the determinant. Determinant, you can also try to use other rows. It doesn't necessarily that you must use the first row. You can also use the second or third row. But then in this case, your cofactor is going to be different. So you have to be very careful, because like for example, if you use this row, you must remember that this is negative. The cofactor of this is going to be negative, positive, negative. Right? So this kind of thing you have to be very careful, but now you can use any of the rows. Okay. Okay. Question number 1, which is kind of like a recap of what you have learned. Any question? Any questions? Semua diam. I hope I'm not enjoying it by myself. Tak shot sendiri ya. I hope there's no problem. Then if there is no problem, now let's go to the second one. Let me just show you the screen, so that I don't have to write it on the whiteboard here. Okay, so the second one. Here, I ask you to do the same for matrix B for question number 1. So this is straightforward. I won't give you the answer here because this is, I'm sure you can do it. Okay, but question number 3 now. Question number 3, they ask you to find the commutator of matrix A and B. So commutator of matrix A and B is given like this: AB minus BA. Nak darab matrix ni tak ada problem juga kan? No, right? Very good. So no, then we can save time. So here, what is important is that this is especially used in quantum mechanics. You will see when you go to the 3rd year, 2nd semester, you will have to do lots of this kind of things. You have 2 operators, right? So operators, they are represented by a square matrix. So now when you want to know whether you can measure two physical quantities represented by the operators, So you have to find the commutator of these two operators. And how you find the commutator of these two operators is simply AB minus BA. So if this is equals to 0, it means you can in fact measure them simultaneously. In the notes that I've given yesterday, I also use the example of the momentum and the position operators. You know the position and momentum of microscopic particles. You cannot know them precisely because these two operators does not commute, right? So the x operator and the p operator does not commute, and therefore you have the Heisenberg uncertainty principles. So if you if you want to know more about what I'm talking about, you should look at the notes that I've shared with you yesterday. So number 3, I think this is considered done. So number 4. Number 4, I think you might come across this another new term, which is a skew metric. So is C a skew matrix? So what is your answer? Yes or no? What is do you think C is a skew matrix? Skew symmetric. Yes or no? Yes. Let's see. I have new answers here. Yes. No. Skew matrix. Let's say. Aij equals to minus Aj. No. Right. Very good. Tak kisah whether you're correct or not. I love to have a reply. So here you have 1. What was that? I minus 1. Okay. So let's stop sharing and I go back to my disk. Okay. So a skew symmetric matrix is when you have Aij equals to minus Aji. So Ij, you change the row and column, which means you transpose the matrix, and then you want to make sure that these two are the same. So here Aij, if let's say you have 1 1, so the if you change, you still have 1 1, right? So there is no big deal. 1 1 and 1 1 is the same. Right, but here if you change 1 2, okay, so I equals to 1, j equals to 2, then now you're going to look at A12 is this one, row number 1, column number 2, okay, and you're going to change this to 2 1, so 2 1 row number 2, column number 1, so it's this one. So here you see this is I, this is minus I, which fulfills this one, right? So therefore, C is a skew matrix. Skew symmetric matrix. Sorry, I keep on hitting the symmetric word. So this is a skew symmetric matrix. Skew symmetric matrix. Okay. Boleh semua? Okay, very good. So, so this is a very easy example. If you look at this one, for example, now, so is this a skew symmetric matrix? Is now a matrix, is matrix A a skew symmetric matrix? No, right, Farhan, good. So this is not a skew symmetric matrix because now you just have to compare these two, and this two, right? So 0 6 is not the same, minus 1 2 is not the same, 3 minus 1 is not the same, right? So this is not skew symmetric matrix. Next one is C is C a singular matrix? So is C a singular matrix? Yes, no? You just have to take a shot. No. Farhana say no. What about the others? So we have one node here. Here, that's so singular matrix. You answer me first, I tell you. If the yes, very good, very good. So determinant, if the determinant is equals to 0, then you have a singular matrix. Okay. So yes or no? Shahida, no. Betul. Khalida, no. 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 Equals to -2. Let's see. Let's see. Right? So here you have -1, and then here you have minus, but plus I squared minus 2. Okay. Right. So just double check. Did I give you the wrong one? No. Right. Correct. Yes. So in this case, this times this is -1, -1, minus, and you cancel with this one. So this is I squared. So -2. So the determinant is not equal to 0. But now the most important thing is if the determinant is equal to 0, of course, it's a singular matrix. But the proper one is that C, if, let me just write in full. If C is not invertible, okay, if the matrix cannot be inverse, cannot be inverted, and then that is going to be a singular matrix. Okay. So in this case, a determinant is non-zero. You should be able to invert this. So therefore, this is not a singular matrix. Okay, boleh? Bagus. Yang lain okay? Yang lain? Okay, Farhana. Okay, right. Okay, very good. So now let's go. Yes, Umi Hanifa, thank you so much. My Sarah just came in. Okay, good job, Sharo. I hope. So let me just present a window now. What happened to my screen now? Okay, so conjugate, you can do that. Okay, the conjugate of this, the conjugate of matrix C. So conjugate, and sometimes you have to be very careful. Okay, conjugate, adjugate, adjoint. So in matrix, normally they call adjugate, adjugate or adjunct, because adjoint sometimes they don't use it anymore, because adjoint matrix can refer to the matrix of the adjoint operator. Okay, but I forgot about it. So you have adjunct, adjugate, and then you have to differentiate it whereas against conjugate. Okay, conjugate is like a complex conjugate. So here you just change the sign of the imaginary part. So the conjugate of C is minus, in this case, this is minus I, this is I. So you just revert the sign, okay? Not to be confused with, oh, I did it right, adjugate, adjunct, adjoint, okay? Okay, so now let's go to number 2 now, which is sets of linear equation, homogeneous equation, row reduction, and rank of matrix. So this is the part where Kishan mentioned that it was a little bit messy. So yes, it is when you go to the row matrix. Okay, so here what I do is I just give an example like this. You have the 3 sets of equation, linear sets of equations. So let me just ask you, normally when you learn in linear algebra, they keep on saying linear, 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 but what does linear means? You know, can here they say this is a linear set of equation, right? What is linear? You can solve linear equation, but what is linear equation? Just to refresh our mind. Okay, here, wait. Faris asks question, adjugate. Yes, this is how you spell adjugate. A-D-J-U-G-A-T, adjugate. Or adjunct, A-D-J-U-N-C-T. Okay, Faris? Okay, very good. So what is linear equation? Ax plus b. Good try. Good try. Proportional. Let's say ax plus b. Ax squared plus y. Ax. Ax plus y squared. 1, 2, 3. Which one? Oh wait, which one? Which one? Oh, which one is linear and which one is not? Kishan says straight line on the plane. Okay, good, guess. Highest power of root equal to 1. Highest power of root equal to 1. Okay. Right. A lot of people say number 1 is linear. Number 2, is it linear? Number 3, number 4, number 5. Ada jawapan lain? Semua satu saja. Yang lain tak ada. Faris semua satu. Beatrice satu, Omi satu, Faris satu. Kishan straight line on the plane. Later I answer. Okay. Shahrul, highest power of root equal to 1. I don't understand. Sorry. Okay. Ada jawapan lain? Shahrul, Kishan, give your another shot. Yang lain. Shahrul no, 1, 2, 3, 4, 5. Oh bukan. Let's say sebelah kiri. No, wait. I'll tell. Shahrul 1, Faris 1. Raja, I didn't hear anything. Raja, where are you? Raja, Daryl is not here. Daryl is not here. Okay. Kishan say, I think all of them are linear. Okay. So 1 to 5 now. Okay. So now if you search, I think you can find the answer. Right. So f, let's say you have a function f x y. So if let's say you see something like this f x y, it means this f is a function that depends on x and y. Okay, that is how we understand it. This f is a linear function or linear function of x and y if you can separate it into like this. If you can separate it into a function that depends on x alone and a function that depends on y alone, and this is f is therefore a linear function, a linear equation. The ones which has exponent are not linear, not necessary equation. Okay, but good try. Good try. Let's say, Kishan say a function that has exponential is not linear. So here, if I give you something like this, f x y equals to, just for the sake of simplicity, I just take minus x. Okay. So here, is it possible? Is this a linear function? If you compare this with, let's say this is f1, this is f2. Let's say you have e minus x plus e minus y, right? So both you have exponential term, right? But this one, this is non-linear, this is linear. Why? Because I can write this as fx, and this is fy. Okay. Okay. So what? So now, if you understand this, if you go back now to this example here, 1, 2, 3, 4, 5. Which one is linear? Which is not linear? One, two, three, five. 1, 2, 3, 5. 1, 2, 3, 5. Yes. Okay. 1, 2, 3, 5 is linear. Here you see, this depends on x alone. B is just a constant now. Okay. This is a linear, yes. Ax squared nampak macam very complicated square, tapi this depends on x alone. This is another function which depends on y alone, linear. This as well, although I just put a square here, it's the same. This is not, because here you cannot write this as fx plus fy because they're multiplied, right? And this is linear because this is fx, this is fy. Okay. So that is linear. Yeah. So this is linear equation. So linear equation here. Linear equation here, you can write them in terms of a matrix because how should I say? Let's say you have a function fx. Let's say we just for discussion, we say fx is a square matrix, fy is a square matrix, right? So fxy, you can just, this is a square matrix, so you have 1, 2, 3, 4. So you have a 3 by 3, and then here you have a 3 by 3. Okay, so you just have to plus them together and you can write this as a function f. Or inversely, you can say that function f, I can break it into 2 matrices. Okay, so if you have a non-linear one, like in this case, there is no way for you to write it in terms of these matrices. Okay, so that's why in your linear equations, you can use a matrix in order to solve it. Okay. Oh, I forgot that I didn't change the screen. So I hope you can see this clearly in your laptop. Right. So now let's go back to the PDF. In the PDF, here they give you a linear set of equations. You have 3 equations here, and now you have to check you have how many unknowns. Okay, kalau kita ada multiple sets of equations, you can have tens of sets of equations, but you must still know how many variables that you are trying to solve. Okay, so in this case, you have three sets of equations and you have 3 unknowns, and from these 3 sets of equations, you write it into a matrix form, like in this one, equation number 1. So from here to here, saya rasa semua boleh buat because this one is very standard. I think in linear algebra class, they have already really trained you on this one. From here to here, you just have to arrange it nicely. So you have x, y, z, x, y, z, x, y, z, and then you just have to put the coefficients, all the coefficients on this according to the place where they appear, and then on the right hand side you have the unknowns x, y, z. So here you can see that 2 times x, you have 2x plus 0 minus z equals to 2. So if you arrange it like this, you can get back these sets of equations. Okay. So here I say this is this square matrix, let's call M, and this is V, this is K. So we want to solve for V, right? So here the standard way is you can just use the inverse matrix. Okay, so let me just let me just okay, so I just want to emphasize the order of the matrix. I think you already know this. So here, in order to kind of like get rid of this M over here, so you multiply M by its inverse. So since you are multiplying on the left hand side, so you have to multiply here also on the left hand side. Okay, so this and this is 1, so you have V equals to M minus 1K, right? So that is how you get this equation number 2 over here, number 2 in the PDF. Okay, let me just give me a minute. Okay, right. Okay, so now let's go to the questions. So here they ask you if this is a homogeneous equation. So is this a homogeneous equation? Yes or no? Is the equations that I give you here a homogeneous equation? Yes. Faris kata yes. Okay. Who else? Fitri don't know. Alia, I'm not sure. Anyone else? So linear functions, please remember the meaning of a linear functions. Next time after other lecturers they teach you, you please tell them, yes, I know what is linear function. Okay, so now homogeneous equation. Is the equation that I give you homogeneous or not? Yang lain. At least say yes. Faris say yes. Fitri don't know. I'm not sure for Alia. What about the others? Sharul, Raja, diam. Raja, where are you? Khalida, Amilin, I saw her just now. Anis. Let's see, somebody. Amilin is answering. Yes. Not sure. homogeneous equation has derivative. Nope, not so difficult. Equation is simpler than that. So we have a deal after this. Next time when people ask you what is a homogeneous equation, what is linear equation, you can tell them. Okay. So a homogeneous equation is an equation where you have x plus y equals to 0. Don't care. 3x plus I don't know what 2y equals to 0, which means I have something like not nice. Let me just use another one. Can. So let's say I have these two sets of equations. So I change this into matrix. So this is going to be 1, 1, 3, 2, x, y equals to 0, 0. Okay, I don't care whether this can be solved. That's not my point now. My point now is if I have x and y, I arrange all my functions over here, x and y, and this f plus y or whatever it is going to be equal to 0. So this is a homogeneous equation. Okay, homogeneous equation is anything over here. This is 0, 0, 0. Okay. Okay, ingat Yeah. Okay, Kishan. Ax equals to 0. Very good. So linear function, linear equation, linear function, linear equation. Ini definition dia. Homogeneous equation ini maksud dia. Apa-apa dekat sini kosong. Okay. Very good. Right. So here, so in this case, you see this equation in the PDF here. So equation number 1, of course, this is non-zero. Sorry, on the right hand side, this is non-zero. So this is not a homogeneous equation. Okay. Right. So now let's go to the next one. So A, I ask you whether this is a homogeneous equation. No, the answer is no. So for x, y, z, again, I don't go into the details because you should be able to do this. So x, y, z you boleh cari kalau rasa susah sangat guna. For me, if you use this matrix form, this is very very straightforward. Kalau tak, kita guna macam apa yang kita pernah belajar juga. Wait, I need this. What you do is you kind of like multiply this and then you try to hapuskan, you cancel all the functions and leave only with one, and then you can find what is that function, and then you put back into the other equation, and then you find the other function. So this is kind of like this is actually the row reduction method. It appears like a row reduction method. Okay, so right, so number 2 is done. Number C. Suppose now we want to solve the linear equation using row reduction method. Okay, so now you want to use a row reduction method. So I ask you to write the augmented matrix for the set of linear equations. Apa itu augmented matrix? What is augmented matrix? Fitri, linear algebra notes yet. So I don't think I should go through all the things that you have learned last time, right? So now it's just to kind of refresh all that you have learned. Okay. So I think your mathematics lecturer should have covered a lot of things during one semester, right? Okay. So what is an augmented matrix? Okay, so now I need to run this one. how does the augmented, yeah, augmented AB, BA, very good. Same answer. Okay, so augmented in this case is going to be 2, 0, minus 1, 6, 5, 3, 2, minus 1, 0, right? So sometimes they have a line over here, but if you don't have line, this is also perfectly fine. Okay, so this is the augmented matrix that you have, that you write. And now you want to do a row reduction method. So let me just go down. Okay, so now they ask you to find the rank of the augmented matrix. Okay. So what is the rank of the augmented matrix that you have found? Apa jawapan? Yeah, accidentally muted mine. Okay, so here, in order to find the rank of the matrix, right, you have to do a row reduction first. You have to, the whole idea is you need to change this into situations where you have like this. Let's say 1, 0, 0, a number, 0, 1, 0, a number, let's say a number, 0, 0, 1, a number, right? So in this case, after you have row reduced it to this situation, you have a diagonal. So in this case, let's say this is my x. So my x is going to be this value, my y is going to be this value, my z is going to be this value. Okay. So in this case, the rank of the matrix of the augmented matrix in this case is 1, 2, 3. So 3. Okay, the rank is 3. Tapi kalau yang ini kosong, let's say this one is 0. Okay, ataupun sini kosong juga. Because if this is 0, this one doesn't make sense, right? So this one is it's not counted. But if this 0, 0, 0, 0, okay, this is even easier. 0, 0, 0, 0. So this one is not counted. You only have rank 2. Okay, faham tak? So kalau semua kosong, ni rank 2. Kalau tiga-tiga ada nombor, then this is rank 3. Tapi kalau macam sini kosong, this is like x plus y plus z equals to a number. Tapi kalau kosong plus kosong plus kosong equals to a number, tak mungkin lah. Right? So this one is also not counted. Okay. So here, kalau ni 1, 1, 1, sini semua ada nombor, right? So this is rank 3. Okay. So I need to take a short. I need to break for a while. Can I leave you all with this and you try to find for me what is the rank of the matrix? Okay. Then later we come back to this. We take a 2 minutes short break. All right. Thank you. So you do first, and then later we will compare our answer. Okay? Right, sorry, I'm back. So have you managed to get the answer? Yep. So Faris dapat berapa? M1. So let me just write the answer on the whiteboard here. So let me just go here. And not sure that. Right. Okay. So let me. So here, let me just show you the. Let me see. Where do I go? Can you see this PDF version here? The answer that I'm showing. Yes, very good. Right. So here, let me show here. Yep. So this is in the Boas book. So there is this is the way that they try to solve this. So just now I was doing another way on the whiteboard, but then I scrapped it because it's longer than the place that I allowed to do. So here I also get things like this 0011, right? And you have these numbers. So the whole point here is that you want to um, change this sets of metrics from this is the actual metrics over here, and then you want to reduce it to all right. You want to make the other terms, the other elements to be equal to 0, and then you just retain the diagonal terms. And then in this case, you have this is your answer that you want 3 over 2 minus 1, 1. Okay. In the where did it? So when I was doing, I got 0, 0, 0, 11, 11 in the second row. So there is no fixed rule in solving this. Huh? So when I got it 0, 0, 11, 11 at the second row, and then this one 0, minus 1, 1, 2 is at the third row. So what you do, you can actually shift the matrix. You can shift the rows of the matrix. So since 0, 0, 11, 11 is in the second row, but the first two is 0, right? So you can shift it down and you bring this one up, and then you have to finish off the other two remaining one to be 0, and then you get this answer here. Okay. So this is a row reduction, which is rather tedious, long to show. Okay. So let's go to this one. Okay. So now here, this is the answer given in the book. Let me see. What? Right. Right. So let me show. Okay. So now once you have row reduce this guy to this, right? So you row reduce this guy to this guy, um, and then we call this as a matrix that A matrix A, right? We just call this as matrix A. And now this tree over here, this is my, let's call this as the matrix M in the book that I mentioned here. So the augmented matrix in this case, this is rank 3. And then the the matrix M, which is this part only, this is also rank 3. Okay, so augmented rank 3. This one is also the matrix M that I mentioned here. This is rank 3 as well. So in this case, rank 3, how many unknowns? You have 3 unknowns, right? So in this case, you will have one solution. That is, this is the only solution that you will have. Okay, so that's why I put this here. This notes on the box here. So basically, why do we need to know about this row reduction is right. So here we want to determine whether we have a solution. You have one solution or you have many solutions, right? So if your rank of M is lesser than A, so rank of M lesser than A, so it means if you take for example this rank. This augmented matrix. So in this case, this is rank 3, right? Rank 3. But then if let's say for example this is 0, okay, so this is 0. So your this matrix M over here, the rank is 2. Okay, so in this case, the rank of the matrix M is lesser than the rank of the matrix the augmented matrix A. And therefore, you have the first condition here, which is here you have no solution. Okay. Boleh faham? Right. So if let's say in this case the second situation or the second row here, your matrix M, the first 3 columns, the matrix M is 3. The augmented matrix, the rank is 3. So here you have only one solution. Okay. And especially this is the case for homogeneous equation, right? Then if my rank of M is equals to A, but then lesser than R, okay, so what it means is that let's say my third row, let's say my third row, I row reduce it, and at the end I have 0, so all 0 here. So in this case, my rank of my matrix, the augmented matrix, which we write as A here, is 2. So the rank of the matrix of M is 2, right? So in this case, rank of M is equals to 2. Rank of A is equals to 2, but the number of unknowns is 3. Okay, so in this case, I can have a solution, but my solution will be based on the remaining unknown that I don't have answer. Okay, so that's the meaning of this 3 selection rules here. Okay, everyone. So the whole point of yes, JDM2 number of lines. No, sorry. Let me just what I call the matrix M is here. The initial this is actually this matrix, the initial matrix, and this is the augmented matrix, right? So if you row reduce the augmented matrix, So in this case, you will have the rank of the augmented matrix. So assume, don't forget about this one. So assume that now in this case, the last line or whatever line, this is 0. So the rank of this augmented matrix is 2. And then the matrix n that I mentioned here is just the first 3 columns here because this is the initial one. So if this one, if you row reduce it and then you have 2, so in this case 2 and 2 is the same, 2 and 2. So there is possibility to write an answer, but then your answer is going to be based on the one of the variable that you cannot find. Okay, which means, let's say for example, you have something like an x plus y equals to z. So you have to write your answer based on one more variable. Volumetric, boleh Faris? Right. So basically, there's a whole point of this row reduction procedure because now in nowadays you don't have to use row reduction method in order to find the answer, right? You can like this example, you can just solve it by matrix very easily. If you want, if you have the computer, you have the software, you know how to do some programming, you can easily find the answer. But then in situations where you have things like this, right? You have things like this, and then this is not possible to get the answer by computer, and you have to do some calculations by hand. Or even in this case, if let's say this is not 0, but this is, let's say, 1, and if you don't, the computer is not going to tell you that there is no one answer, right? Because in this case, this is rank for my augmented matrix. This is 3, but the rank for n is going to be 2. Okay, 2. So this is not consistent, right? This is not consistent, and you have many solutions. And so your computer is not going to tell you about this. So that's why you need to know some basics of using this row reduction method. Right. Okay. Let's see. So the answer here is in this PDF in the Boas book here. You can try it on your own. So it's fun to do it, although it's very tedious. Then here. So, and then I put another box here to mention about the homogeneous equation. So homogeneous equation, remember you have x plus y equals to 0. So the trivial solution, what they call as trivial solution, is everything equals to 0. So then you don't have to solve anything, right? So that's what they call a trivial solution. But for homogeneous equation, you will have a solution other than the trivial solution. So it means you don't want everything equals to 0, so there's no fun in it. So you will only have a solution if your determinant is equals to 0. Okay, so yeah, so this is important to know, because if you have a homogeneous equation, you must first check that the determinant is equals to 0, and if the determinant is equals to 0, then only you will be able to have a solution, right? Okay. So here I say let's try to solve for the following two sets of linear equations. Right? Dah cuba buat. So maybe you can try this on your own first. Let's go down so that we save some time here. So there is another interesting fact which I want to point here. And this was also discussed in the book, and that's why I say this book is very nice. So here they talk about a determinant. So sometimes you have a determinant, and then before you try to solve for the determinants, you must look at the matrix first. Okay. So the matrix here, if you look at this example, this is row number 1, 2, 1, 3, row number 2, 5, minus 3, 2, row number 3, minus 4, minus 2, minus 6. Here you will see that the row number 3 is actually twice the row number 1. Okay. times -1, right? Faham tak? Maknanya daripada sini ke sini kita darab dengan -2, right? Sorry, the other way around. So from here to here, from row 1 to row 3. Row 1 you multiply by -2, then you will get -4, this one -2, 3 times -2, -6. Okay, so in this situation, your determinant is 0. So you tak payah buat calculation, you know this is equals to 0. So the same goes for column. So kalau column, let's say contoh kalau column ni, you can multiply by a certain number and then you got this column, right? So in this case, the determinant is also equal to 0. Right? Pernah dengar, have you all heard of this rule before? Oh, pernah. Oh, okay. All right, right. Very good. So this is kind of a repetition. Right. So okay. So this is the example. Then the last one is to diagonalize the matrix. So here, you want to diagonalize the matrix. You should be able to do that, huh? So, pernah belajar kan how you diagonalize the matrix, right? So let me see. Should I show this? So to diagonalize the matrix, let's say, so in diagonalization, in this case, you will see a lot of applications in quantum mechanics. You will do a lot of this kind of thing, right? So let's say, what should we do? So let's go with this matrix B here, 230. 230, 320. So 001, right? Let's stop sharing and go to here. So if you no, yeah, okay. If you go with this matrix, you want to diagonalize the matrix. So you know this, you know this the steps. You just have to take 230, 3, 2 minus lambda, 0, 0, 0, 1 minus lambda. So you have to set the determinants to be 0. So in this case, you have 2 minus lambda. Yes, 2 minus lambda. So in this case, you have to take the cofactor of this. So the cofactor of this is 2 minus lambda, 1 minus lambda. In this case, let me just write this. So this is 0. Okay, and this is -3. So -3. So in this case, here you have here, right? So you cut off this one. So you have this guy. Here you have 3 times 1 minus lambda. Okay, so -0. So here you have 2 minus lambda squared, 1 minus lambda. So here you have minus 9, 1 minus lambda, and this is going to be equals to 0. Right. So please do for me, what is your lambda here? What is the eigenvalue that you have for this matrix? Please find for me the eigenvalue for this. -1. -1. What else, Faris? Gonna expand. Yes, of course, you have to expand. You have to. It's safer if you. Yeah, you should. You should expand this guy, and then you multiply them, and then you plus them because here you have a 9 over here. This is not the same as like like a complex equation. You have x squared plus y squared minus I 2xy equals to 0. Okay. In this kind of equation, right? So you have this part and this part to be equals to 0. So in this case, you can put x squared plus y squared equals to 0, and separately you have 2xy equals to 0, right? Because this is imaginary part, this is one part, and this is another part. But in this case, you have to expand that, and you have to be very careful with the numbers. Decimal boleh. Decimal. I don't think the answer is a very nice clean number. It's just an integer. Syahida jawapannya integer saja, tak ada decimal. Let me just have a see. No. This is difficult to use. Right, 5 minus 1, 1. Yep. Good job, Syahida. Good job. So jawapan negatif 115. Okay, so let's do for another one. The next one. What is the answer for the matrix yang ketiga? the third matrix. Let me just write down here. 1, 2, 2, 2, 3, 0, 2, 0, 3. So what is the eigenvalue? So this one you have 1, 1, 5. Yang lain dapat tak jawapan? Just let me know if you have get the answer just for this matrix. Dapat. So what do you get, Alia? Alia dapat untuk yang mana satu? Yang this one or this one? First study. Oh, very good. Okay, good job. So now, if you do the second one, what do you have? Who got the answer already? You should get -1, 3, 5. Okay. The second one, if you diagonalize, you find the eigenvalues. This is -1, 3, 5. Okay. Siapa dah dapat? Dan one person got it, then we will go on to the next one. Faris, okay, Faris, you got the same answer, right? -135, right, Faris? Yep. Okay. Very good. So, so I assume the others also will be able to get it. So now, just to recap, other than just finding eigenvalues, you must be able to diagonalize it. So when you say you diagonalize the matrix, it means you will get a nice square matrix with the diagonal values, non-diagonal equals to 0. Okay. So how do you get this? So from, let's say we use the first example, you get -115, so you have to put in one by one, right? So let's say if you put lambda equals to -1 into this equation, so here you have 2 minus -1, so you have 3, 3, 0. So you have 3. This is 3 again, 0, 0, 0. 1, 1 minus 1, so this is 2. And then you have x, y, z. So this is going to be 0, 0, 0. Okay. So here, how many unknowns do you have? You have 3 unknowns, right? What is the rank of this matrix? What is the rank of this matrix? What do you think? How does one say? If you put in lambda equals to -1 into this, then you have this equation, and then you multiply by an eigenvector that you want to find, and this should give you 0, right? So there is 2 ways that you can do this. That is, you find the eigenvalue. Eigenvector, sorry. So one is you take the matrix. Let's call this as matrix. What should we call? Let's call this as matrix A. Okay. Let's call this as matrix A, and you can put matrix A multiplied by x, y, z, and this should give you the eigenvalue that you want. Okay, and this eigenvalue that you want. So this is one way to do it. Okay, so it means here you have 1, 1, 1. This is a square matrix, right? So it means you take 2 times x plus 3 times y equals to lambda 1. So if lambda equals to -1, so this is going to be -1. Okay, so that is one way that you can do to find, that you can use to find the eigenvector. Or the other way is you use this form, and then you multiply by the eigenvector again that you want to find, but this is going to be equals to 0. Okay, so this is the first way that I do. Right. So now my question is, now if you have this equation, you have this matrix. So what is the rank of this matrix? What is the rank of that matrix? Two. Yeah, very good, Hanifa. Hanifa. This is rank 2 because this and this is the same, so you can cancel them. So at the end, if you do a row reduction, right, so this is going to be 3, 3, 0, x, and this is going to be 0, 0, 2, z, and you have 0, 0, 0, y. Right, so actually you don't have to write the x, y, z. So this is rank 2. So remember what we talked about just now. You have 3 unknowns, but you have rank 2, right? So it means here you will have to write your solution based on the third one. Okay. So here you can have 3x plus 3y equals to 0. 3x plus 3y equals to 0. And then you have 0, 0, and then you have 2z equals to 0. Right. So here, if you look at this, this looks like an equation of plane, right? Betul tak? Remember when we studied the first chapter on the vector, we said the equation of plane looks like this. So you have 3x plus 3y equals to 0. Right? Something like this. This is the equation of plane. So in this case, this is z equals to 0. So this is also an equation of plane, right? Okay. So here, so now you have something like this. So x and y, there is no definite. There's no definite answer, right? So what you can do is you just have to you can reduce this to x plus y equals to 0. Okay, so x plus y is equals to 0. So this is the equation of plane. So you can choose any points that is on the plane, and that will be the solution that you want. Okay, so for example, you can take x equals to 1, and then y is going to be negative 1. And then you have z equals to 0. So now you have 1 minus 1, 0. So let's call this as V1. So this is the first eigenvector. Okay. So any questions, any problem? Comments? So then you do the same for lambda equals to 1. So now you have 2 minus 1, 1, 3, 0, 3, 2 minus 1, 1, 0, and 0, 0, 0. All right. So here you have x, y, z equals to 0. So here you have x plus 3y. This is going to be equals to 0. Or you can have 3x plus y equals to 0. Okay, so this again you have a rank 2, but then you have 3 unknowns, right? So here 0, 0, 0, 0 equals to 0, right? So here z is not necessarily equal to 0. Okay, dia kosong kosong kosong, darab z sama kosong, z tak semestinya kosong. Okay, z there is a value. Okay, so here you can again, this is the equation of plane. You can choose a point for x, and when you define x, you will find what is y. So this is the equation of plane for this one. So let's say if you choose let's say y, what should you do? So if let's say you choose y equals to 1, so you have x equals to minus 3, right? So here you have x, y, z to be x equals to minus 3, 1. So z is equals to any value, right? So that you can choose 1 or 0. Okay. Right. So this is V2, right? So this is V2. V2. And you do the same for lambda equals to 5, the next eigenvalue, lambda equals to 5, you will get V3. And then now you can combine V1, V2, V3 into a matrix. Let's call this matrix as C. Okay, so here you have all the terms over here. So you have V1, V1y, V1z, V2x, V2y, V2z, and the next point here. Okay, so then you will get this matrix C, which you combine all these eigenvectors, and then in order to what we call to diagonalize the matrix A, you will have to find C, the inverse of this matrix, multiplied by A, which is the matrix, the initial matrix, times C again. So this one will give you a diagonal matrix that we write as D. Okay, right. So I let you all to do this as an exercise. How many questions here? Let's see. So there is 3 metrics here, diagonalization. So I leave this for exercise and you submit it next week. Or maybe by Wednesday. Okay, Wednesday. Boleh? Boleh kan semua? Boleh. No problem. No problem. Because this is just an exercise to refresh. Okay, so this is done, diagonalization. Diagonalizing, let's say, right. Right, so now eigenvectors again. So if let's say you have already found the eigenvectors, if you use this matrix and you multiply them by the eigenvectors, you should always get back the same answer. Okay, so if you didn't get back the same answer, it means the eigenvector is not the correct one. Let me just rub this. So let's see. Yeah. So let's say if you take A multiplied by V1, let's try this, V1. So let's say we take 2, 3, 0, 3, 2, 0, 0, 0, 1, and you multiply by 1 minus 1, 0. Okay. So here you have 2 minus 3, 0. And then you have 3 minus 2, and then 0, 0, 0. Okay, so here you will get minus 1, 1, 0. Okay, and then now you can take out minus 1 here, so that you have 1, minus 1, 0, and 1 minus 1, 0 is exactly the V1. So now this is negative 1, V1. Okay. So what I've done is I take a matrix representing the operator, in this case operator of matrix A, times V1. So you will get back an eigenvalue of this eigenvector with the eigenvector. Okay, so this is my eigenvalue equation. Okay. So if you repeat one more time, you will again get the same eigenvalue multiplied by the eigenvector. Okay, boleh semua. So this is a very important concept. Once you have the eigenvector, you take A, the initial matrix, and because in quantum mechanics, the A which is something that you want to measure, they call it operator. So this operator, if you take the operator multiply by the eigenvector, it will always give you the eigenvalue associated with the eigenvector. Okay, so if you replace the next one, you should be able to get back the same eigen value. Okay, can? Right, so I guess a lot of people are tired now. So let's wrap up this session. This is what I've mentioned in this column here. So we multiply by you multiply the matrix with the eigenvector, you will always get the eigenvector again. And then yeah, so let me just mention here in this box diagonalization of matrix here. So so here C and this matrix C and D. So C, this is a square matrix, D is also a square matrix. And if you look at the book by Boas, Mathematical Methods by Boas, page 151, they actually describe to you what is the meaning of this matrix C and D. So this is kind of like a rotation. You start with the axis. So n is with respect to a certain axis, and then you kind of like rotate it. What we call that? You rotate the matrix to the direction of your eigenvalue. So like just now, you have eigenvalue -1, 1, 5. So once you rotate the matrix, so you go to the direction of this eigenvectors. Okay, so maybe you should read 151 to make it easier. And now if you have a Hermitian matrix, so I hope you remember what is Hermitian matrix. Hermitian matrix, if you compare this and this is the same, except for here, this C is inverse matrix, whereas this is adjunct matrix, adjunct matrix, right? So here, why they write U instead of C is because U is a unitary matrix. So instead of writing C, they put it U. Okay, so I really want to go into this, but I'm not sure whether you have the mood to go through it again. Let me just check with you. Have you all heard about this Gram-Schmidt method? Gram-Schmidt method. Pernah dengar? Pernah belajar? Pernah? Okay, very good. Wow, nice. Right, so so here in this case, I give you example of the matrix M like this, given by this one, and you want to find eigenvalues. So you will find 3 eigenvalues, but actually 2 of them are degenerate. It means you have 2 values. Let's say, for example, the eigenvalue is 2, so you have 2, 2, right? You have 2 eigenvalues of the same number with the same number. So in this case, if you have eigenvalues with the same number, it means you have a degenerate case. So degeneracy. So in the case where you have degeneracy, then the eigenvectors that you will find is not orthogonal. So how you want to make it an orthogonal is that you find first for the eigenvectors where it is not degenerate, and then after that you have another eigenvector for the case with degeneracy. So now you have 2 eigenvectors. One is degenerate, one is non-degenerate. So you want to find the third eigenvector for the case of a degenerate one, right? So how do you do is you take this one V1, this is V2, and you use the Gram-Schmidt method in order to find the V3. So so it means at the end of the day, you have 3 eigenvectors which is orthogonal to one another. So although this 2 is degenerate, but then the eigenvectors should be orthogonal. Okay. Right. So that's it, right? So for exercise, I'm not sure whether. I guess the others at the top here is very straightforward, so I won't ask for it. Here you just have to do for me the as a homework, right? You diagonalize this 3 matrix 1, 2, 3. find the eigenvalues, eigenvectors, diagonalize it, and then you do it for the next one, which is here, M, and degenerate case, and the last two here for the degenerate case as well. So in total, you have 6 matrices to diagonalize, 3 for degenerate and 3 for non-degenerate. Okay, so I guess this is a quick walk in the park for you. Right, soalan saya dah letak di, I can actually post it back in the e-learning, but it is also given in the link to my website. Okay, dapatkan the link to the website. I'll post it in e-learning later on. But then if you want to do it first fast, you can go to the website and then you get the PDF version. Okay, so I guess this is the last for the metrics, at least for the kind of a revision of what you have learned in the linear algebra class. And then you will see that it can be applied in vector analysis. I'm not sure whether have you learned the equation of plane, and then you use metrics in order to find this equation of plane in your linear algebra class. Did you? Pernah tak belajar? Not sure. Not sure. Okay. Yeah. So I have written this in the PDF. Read through it. Then we will go through it together. On the what we call that, on the vector analysis. We have done this in the first chapter when we talk about how you get the equation of plane. You remember you do a lot of mathematics and so on. So in this case, you can use metrics in order to solve to get the equation of plane, which is, I think, kind of like easy, I guess, easier. And then that is application for vector analysis. And then you will have also application in quantum mechanics. You have done this, so this is very similar to what you expect. In quantum mechanics. And then the last one will be an application on the electronics, which I haven't prepared. I will do it in the next 2 days, I guess. And that is all for metrics, right? So we go very fast because you have done it. So if you have any questions that you are not sure, please post it to me personally if you want, and then we will discuss it in our class, right? So that's all for me today. I give the session to you if you have any questions. Do you have any questions? No? No one will. I just wait for a while more if there's any questions. So about last class, it seems probably some of you might have some slow connection or something. So I thought I waited very long. And then I said, okay, that's it. But then end up someone wants to answer, but it was too quick. So no, sure. Lailato is back. Final Fitri Farhan is final exam confirmed in July. You mean for this paper or for general? Fitri do you mean for this paper or for this paper? Okay. For this paper, For this paper, we are not going to have a final exam in the usual case. Okay, I say in the usual case because in the usual case you have, I give you 5 questions with the many questions and then you solve it, right? So we don't intend to do it that way. But what we will do instead is to do the multiple tests according to topics. So you will have 4 tests. You have test 1 already. Test 1 you have already done it. Then you have test 2, 3. 2 on complex. Test 2 is on complex number. Test 3 is on matrices. Test 4 you will be on the ODE and PDE. So test 4 will be on the last day of, so not on the last day, but on the actual day that they schedule the exam for this paper. Got it? So test 2 soon. Test 2 will be next week. Test 3 will be in the end of June. Test 4 will be on the day of the final exam. Yes. So test 4 is the date of the final exam, but it's not the final exam, It's one of the tests that will contribute to the marks. Okay, so test 1 10%. Test 1 10%. You got the numbers. Test 2 10%. Test 3 10%. Test 4 will be 20%. So that will be a total of 20%. 50%. So another 50% will be from assignments, which, for example, the one that I just uploaded yesterday, it was on complex number, and previously you also have done the assignments for vector analysis and vector calculus. So you have 2 sets of assignments. The next one, what is that? Metrics. You have another set of assignments for the EPD and another set of assignments. So that will be a total of 100%. Boleh? So so patutnya boleh score yeah. So but the most important thing is to do your best. I think the setting, this kind of setting will be good in the sense that you can focus on the topic, master the topic well, and then just take the test. Okay. Okay. Right. Right. So to me, like especially in this matrix, this is very it's very obvious because you have already taken it just recently, and you are still fresh in your mind. So you still retain this information, right? So you can do well. What I'm more interested is to kind of like show you how you actually apply all this mathematics and physics. Okay, so behind them is the technical part, like this one, how to diagonalize matrices and so on. So that is the technical parts which you already learned. Yeah, it's nothing new, but it's just to reinforce your skills, right? And I really hope that you don't kind of like forget about you can forget about me, it doesn't matter, but you don't forget about the mathematics, all this stuff at the back here, because you will use it a lot in other courses. There is this guy who one of the seniors who went to Japan, to do some internship. So even if he was doing something which is kind of like an extension of what you learn here. So he when he came back, he kind of like mentioned like this mathematics that you learn, for example, equation of plane, it's like a very common, right? But then you actually use the idea to do it for other more sophisticated topics, physics, right? So you start with the basics and then you go further. Okay, so please retain whatever you have learned. So what we call that just now, linear equations, homogeneous equations. You should be able to know by heart. If people ask you next semester, you say, yes, I've learned it before. I remember it before. I remember it. Okay. All right. So yeah. So enough of rambling by me. So I guess there is no other questions. No questions going once. 1.5, 2, 2.5, 3, and that's it. Okay. So thank you very much for participating in today's session. We will meet again on, yeah, I think Wednesday will be good. Wednesday, and then we will go through the application in vectors analysis, in quantum mechanics, and hopefully by then I will be ready with the electronic stuff. Okay. So see you. Goodbye, everyone. Thank you. Goodbye. Have a nice day.